difficult, I'll just abandon it and give you the rule. So the proof of the trapezoidal rule wasn't, I know it was a little difficult, but it wasn't crazy difficult. I think you all understood what was happening. You were adding up trapezoid areas. Yeah. But let's see this Simpsons Rule business. Okay. Well, the rule itself is just a little bit more difficult, but not much. Okay, so previously in maths class, we were looking at the trapezoid rule. Simpsons Rule does something similar, except, so let's take a shape. With Simpsons Rule, what we do is we start with an A, we start with a B, and we pick a point exactly in the middle. Yeah. And we draw it here. Oh, let me put it in red. So here's our first point. Here's our second point. Here's our third point. And what you do with Simpsons Rule is you make a quadratic go through the 3 points. And then we get the area under the quadratic. So you can see that this is much better than the trapezoid because at least it's curved. So we have y equals ax squared plus bx plus c. And here we have our function y equals f of x. So our first piece of business is to find the equation of the quadratic that fits through these 3 points. The first point is a, fa. The last point is b, fb. And this middle point here will be a plus b over 2, f, a plus b over 2. You got that? Yeah. Okay? Oh, guys, come on. Yella. All I've asked you to do is draw a graph and write down 3 points. Come on, shouldn't be taking this long. Wakey, what was your first class? With? So you should be wide awake, ready to go. Okay, I'm continuing in 5, 4, 3, 2, 1, Simpsons Rule. Now, we have our quadratic here, and we have 3 points which we know are on our quadratic. So what we can do is sub these 3 points into this quadratic to find the A, B, and C. So let's do that. So if I sub in the first point, I'll get FA equals A squared plus B A plus C. And if I sub in the last point, I get FB should equal A B squared plus B plus C. And then if I sub in the middle point, the Y is FA plus B over 2. That should equal A plus B over 2 squared plus B, A plus B over 2 plus C. Yeah? Now, let's be clear about what we know and what we don't know. So which letters represent things we're supposed to know? Big A or small? Yeah, so we're supposed to know the A's and the B's and the A plus B's. And of course we're supposed to know the heights, because we know the function. Last time it was x squared, whatever. So we're supposed to know these. So when you look carefully, the only thing you don't know here is the A, B, C, and A, B, C. So you don't have to write this again, but if you want, it's like a linear problem. You have A squared A plus A, B plus C equals FA. And then you have here B squared A plus B plus C equals FB. And then here we have A plus B squared over 2 squared A plus A plus B over 2B plus C equals F A plus B over 2. So we're looking for A, B, C. It's not as difficult as it looks because the C's, they're already ready to cancel, aren't they? Because what could you do with these two equations? You should minus them. If I minus them, what happens? The C goes and you're left with an equation with A and B in it. True? And then what should I do with these two? Minus them, and what will I be left with? An equation with A and B. If you have two equations with two unknowns, can you solve this? Yes, you can get the A and you can get the B. And then once you have the A and the B, you can sub it back in and you can get the C. So it is possible here to get the A, the B and the C. I'm going to skip that because it's just something you could have done in semester 1. The only difference is instead of numbers, we have letters, small a and small b. But the concept is not a difficult one, it's just long to do. So what I'll do is I'll get my program to solve it for me. Okay, what has happened? It's decided, no thank you Stephen. Right, so what I'm going to do is get my program to find the A, B and C, and then I have the quadratic. So just before, while I'm waiting for the program to do that, so let's imagine now I have my A, my B and my C, and I want to get this area here. What do I need to do? I would need to integrate this. So if I integrate from A to B, ax squared plus bx plus c, what will I get? Ax cubed, the area, over 3 plus bx squared over 2 plus cx. So you'll want to write this part down, AB. So this equals a b cubed over 3 plus b squared over 2 plus cb minus a cubed over 3 plus b a squared over 2 plus ca. So we'll need to use that in a moment. Okay, I'll go back to my program now. I'll go back, don't worry. So I want to be case sensitive. Okay. So can you just call out my 3 equations I gave you earlier? What was the first one? A squared, was it? Plus b a squared plus c. Oh yes, of course. Plus c equals fa. Yes? Yes. Right? Yeah. And then the next one is the same except instead of small a it's small b, yeah? And then the last one is the same, except it's a plus b over 2. A plus b over 2. A plus b over 2, like this. Alright, let's see what you can do. Ah, no, that's FA, you fool. Right, I can't type in FA, so I need to call it something like, I need to give it a temporary letter. Let me call it U. You can just write in FA. So that's U, V, and this one here, W, but I'll change them back. Right, solve system, 3 equations, 1, 2, 3, and we would like ABC. So get this. Alright, so it's starting to become quite clear that this proof is going to become extremely long and difficult to do. So we'll skip it. I would at least like to explain to you what this rule is doing. Okay? So, well, I'm skipping it in class, but I welcome you to try and finish it. Okay? You're welcome to try and finish it, okay? So what you would have to do to finish the proof is those values of A, B, C that you got here, you would have to substitute them in to this here. And then after you substitute it and after you simplify it, you'll get the formula. And then once you get the formula, you have to apply it n times, like the trapezoidal method yesterday. But I think the proof is too difficult for the class, or too long anyways. I mean, I could sub my answers into this, into the program, and get the program to finish it. So, I've got my A, B, and C. Oh, so ugly looking. No, I think the proof is way too difficult for the class. So we won't do the proof. We'll do it in this program? Let's put it in. So, do you have this cubic, the area expression written down? Yeah, okay. So, it's A. Here, let me just copy this. Right. So I have my A here. This is A. And then let me put in the B. Sorry, let me put in the B. There's my B. And there's my C. Okay. And then what I asked you to do was we had ax squared plus bx plus c. And then I said let's integrate that from a to b. So I got this. And then what I'm going to do is substitute in my a, b, and c from earlier. So that's on lines 6, 7, and 8. So substitute in for a, line 6. What? That didn't change anything. Let's try that again. Substitute in for on line dot 6. Okay, that's better. And then substitute in for B, line 7. Okay, that's better. And then substitute in for C, line 8. It's starting to get ugly, huh? And then don't forget UV is FA and FB and so on. So you can see that this formula, even with the help of the computer program, is getting quite complicated. But then what will happen is the formula will get quite complicated and the formula will start to simplify down. we will discontinue this. But let me at least tell you what's happening. So what the Simpsons rule is doing is if you have a weird shape, it breaks the shape up into quadratics. So for example, you would have quadratic, 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 quadratic. So it breaks it up into quadratic. Whereas yesterday, what did we do? We broke it up into trapezoids, straight lines. So which do you think will be more accurate?
Curves.
The curves, because at least it fits it a little bit better.
But Stephen, here I cannot get more than 3 points.
What do you mean?
Only 3 points. A, B, and one in the middle, exactly in the middle.
Yeah, so what's happening here is you break it up into the pieces, and then the formula makes a quadratic for each piece, using the middle of each piece. So,
I can't get more than 3? 3 pieces?
No, there is I think the n must be at least 3. Yeah. So like if you look at the formula here, n must be an even number. Now remember, we usually start counting at 0. So for example, if I start here at x0, and then I have x1, and then I have x2, these are 3 pieces, aren't they?
Mm-hmm.
The n must finish on an even number, because if you finish here on an odd number, you can make a quadratic, but then you can only make half a quadratic, because you don't have the last piece to finish it up. So yeah, the n must be even. And of course, with the trapezoid, you could do it with just 2. But with the Simpsons rule, has to be 3. Okay, so I'll write down Simpsons rule, but I'll put it down in kind of a bit easier of a way. So Simpsons rule says, if you want to integrate from a to b, f of x dx, you take your h, remember what the h is? The width, and you divide it by 3. And then, like trapezoid, you have the first height, which is FA, plus the last height, which is FB, FA and FB. But what's a tiny bit different now is you have 2 sums here, twice, and then 4. F, X, J we call it, and then F, X, I. So do you remember with the trapezoid, what it was the first plus the last plus twice all the pieces in between. With Simpsons rule, it's a little bit different. It's the first plus the last plus all the pieces with an even I, and then all the pieces with the odd index. I'll explain this with an example, okay? This is an I, and this is a J. Just compare that with the trapezoid rule from yesterday. Do you remember it was h over 2, first height plus last height plus twice all the numbers in the middle, heights. So Simpson's rule is nearly the same, except it has this extra piece here, and you only do the even ones. You don't need the trapezoid one because that was from yesterday. Okay, let's have a look at an example. Let's go back to our example of EX squared. We want to calculate 0, 1, EX squared. So the graph will look something like this. This point here is 0, 1. And this point here is 1E. And we want the area underneath it. Okay, so how many pieces will I break this up into? Well, let's break it up into, well, it starts here. Let's see. That's not quite enough. That's not interesting. So let's break it up into 1, 2, 3, 4 pieces. So this is x0, x1, x2, x3, x4. Did we finish on an even number? Yes, so this is okay for Simpsons Rule. We finished on an even number. Okay. So what Simpsons Rule is going to do, Simpsons Rule is going to put a quadratic on the first tree. So there'll be a quadratic here, and then there'll be another quadratic here. Right, so what we need to work out first are all the heights. Can I go down a little bit? Yeah. Right, so first let's have x0, x1, x2, x3, x4, and then we have our heights y0, y1, y2, y3, y4. And if you want, we know what the x0 is. What is it? Well, I'll write it down here. x0 is a, which is 0. And what's the last one? B, which is 1. And we know the first height. What's the first height? 1. And the last height? E, 2.718. Now, we should work out the h. What's the h here? 1 minus 0 over 4. So what's the h? 0.25. Yeah? Right, so what's the first x1 here? 0.25. The next one? 0.5. The next one? 0.75. Okay. So on our calculator, let's work out the heights. E power x squared yeah. Right, so the heights are 1.0644, 1.284, 1.755, 2.7182. Okay, so let's use Simpsons Rule. So Simpsons Rule says the integration of ex squared dx, that should equal h over 3, 0.25 over 3, the first height plus the last height, plus what's next? Twice, yeah, which one, even or odd? Even. So look, which ones are the even ones? Even one is only actually this guy. And which ones are the odd ones? This one is odd, and this one here is odd. And we don't count this one because this is the first one and this is the last one, which we already used. What? Why 2? So that's 1.284 plus 4 times the odd ones. So that is 1.0644 plus 1.755. So if I hit this in, 1 plus 2.7182 plus 2 times 1.284 plus 4 times 1.0644 plus 1.755 times that divided by 3. So I got here 1.46365. Did we do this one yesterday using trapezoid?
Yes.
And what answer did we get when we did it using trapezoid? Or did I do e to the minus x squared?
No, x squared.
Not ex squared. Or did I do ex squared? What did I get then? Let's see.
0.35.
No, that was x squared. Maybe I didn't do it yesterday. No. I didn't do it. That's fine. Right, let's look at what the exact answer or
Okay, yeah, you did minus ax squared.
yeah, so that's a different one then. Okay. So this is the answer here, 1.462655. And what did I get? 1.463. So you can see that this is accurate to 2 places of decimal. Which is really good. Because we used quite a small number of pieces. We only had here n equals 4. And the area was quite accurate. Okay, so this is good. We have a new method which is a little bit more accurate than the trapezoid. But we haven't talked about the error, how much of an error there could be. So give us the book there. Right, so the error that we could have made, it's similar to the trapezoid, h power 4 over 180 times b minus a times the maximum fourth derivative.
H bar 4 over 180.
Yeah. Now, can I, yeah?
That's the second derivative.
No, that's the fourth derivative. Because the 4 ticks. Okay, can I go to the side for a moment?
Yeah.
So, fourth derivative, fx equals ex squared. Now, life is short, and this formula is not on the exam. So, I don't want to differentiate this 4 times. So what I'm going to do is I'm going to make a very rough approximation. This is what I'm going to do. I'm going to say, well, fx is equal to ex squared, but that's roughly the same as ex. Now it's not, it's different, but at least ex is easy to differentiate. What's the fourth derivative here? Ex, because what's the first derivative? Ex, the second? Ex, so the fourth derivative is ex. And x goes from 0 to 1. So what's the biggest this could be? E1. Right? Because the graph goes like this from 0 to 1. The biggest it could be is e. So I'm going to make a very, very rough approximation. I'm going to say I don't think this will be much bigger than E.
Why?
What do you mean?
No, like,
Why?
why you have taken an approximate value?
Because life is short, number one. Number two, this formula is not on the exam. Number three, I don't want to differentiate 4 times.
Takes time.
It takes time. And then even after I differentiate 4 times, I'll have a look for yourself. Here's the derivative 4 times. Okay? What's the maximum value this can be? Who knows? Let's look at the graph. Sorry, let's look at the graph. Where the heck's my graph?
Maybe you know.
You might have to zoom out. Let me just stick in a Y in case it's complaining about the Y. Oh, so that's not the zoom out button. Right, so my value was way too small. Between 0 and 1 it can go as big as 20.
20.
Yeah, because if you look here, there's 1. So the biggest value is way up here, really high. So my 2.7 was way off. I did too much of an approximation. Let's see if we can make it better than that. Right, does anyone have any other good ideas for approximating EX squared? EX is too bad. No? Any ideas? Could maybe I say it's X squared? No?
It will be the maximum would be 1 then.
Yeah.
Even then it would be 1. E is better.
E was a better approximation than 1.
Yeah. Maybe it's no. 2E.
Maybe I could go with like I don't know. I suppose you could differentiate 4 times and end up with this. So if you differentiate this 4 times, you would end up with that. But I don't want to do that. But now you're making me do it. All right. Let's see how quickly we can differentiate this.
Okay.
Right. 4 times. Let's do it. First derivative. What rule do I need? This is not quick. What rule do I need? Guys, this is our 3rd lesson of semester 2. Yeah.
Sorry, quadratic?
Nope.
No, chain rule.
Chain rule. So this would be 2x e to the x squared. And then the second derivative is product rule, which would be 2e to the x squared plus 2x e to the x squared, which would be, this would become 4x squared. Then the third derivative,
4ex squared.
yeah, no, I'm just writing, this bit will be 4x squared, yeah. Then I would have 4x ex squared plus 8x ex squared plus 8x cubed ex squared. And then finally the 4th derivative would be product here, 4ex squared plus 8x squared ex squared plus 8ex squared plus 16x squared ex squared plus 24x squared ex squared plus 16x4 ex squared. Now what's the biggest this can be between 0 and 1? Well, that's when x is 1. So if I just put in x is 1, that would be 4e plus 8e plus 8e plus 16e plus 24e plus 16e, which equals 4 plus 8 plus 8 plus 16 plus 24 plus 16. So that's 76e. Which is a huge 206.5.
Steven?
Yep.
For the plate and the process will use
Product and chain.
gas and product.
Yep. Alright, so now we actually have a respectable estimate for the maximum. I was only off by a factor of 100. Right, so we go back to our error formula and sub it in.
Okay.
Yep. Okay, I need to go back. Can I go back?
Yeah, please.
Yep. So, let's go back here. Right, what was the H?
0.24.
0.25 power 4 divided by 180 times 1 minus 0. And then what was my maximum derivative? 2.
06.5.
Okay. So you have here that the error should be less than or equal to 0.0048. So what you're saying is the integration of 0 to 1 ex squared dx is equal to 1.46365 plus or minus 0.0048. So you're saying that this is between 1.45885 to 1.46845. So this is what you're saying the true value would be. Okay? Let's look at the computer program. The true value was more like 1.4626. Is 1.4626 in between these numbers?
Yes.
Yeah, 1.4626 is bigger than this and smaller than this. So Simpsons Rule works quite well. What I'll do to finish is let's take out Excel and put the number in. So last time I think we did x squared in Excel, wasn't it? And we got 0.335 when we broke it up 10 times?
Yes. 10 times, yes.
Yeah, so let's do that again, but using Simpsons Rule.
Breaking it up 10 times.
And we'll do it 10 times as well,
Okay.
and see what we get.
I hope we don't do it 100 times.
It's not any more work in Excel to do it 100 times. Let me just close this. Okay, so let's write down, where do we start? It's, well, firstly the A equals 0, B equals 1, N equals 10, H equals B minus A divided by N, so that's the H. So we start with x0, which is equal to A, which is 0. And then we get the next one, which is x1, which will be the previous number plus the H. And then next one would be 0.2, that's x3, and then where do I stop?
When it gets to
When it gets to 1, which here would be x.
Why it's not 2?
Why would it be 2? We stop at b. x3, x4, x5, x6, x7, x8, x9, x10, x11.
No, 0, 1, 3. You missed 2.
Oh, sorry. Oh, that's what you meant by 2.
Yeah.
I thought you were asking me why don't I stop at 2. Yeah, I just skipped over 2. Alright, x6, x7, x8. This is better. x9, x10. Right, what else do I need? I need to know the heights. So the heights, we're using the x squared function, so we'll just square it. So the first height is 0, and then the last height, 1 squared, 1. Now we need to write down the first, the last, the evens, and the odds. So there's the first, there's the last. Right, evens. Even, 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 and then odd, 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 odd. Okay, so let me write out the total for the evens. So that would be equal to this one, plus this one, plus this one, plus this one. And what do we multiply the evens by in the formula? 2. And then the odds? Yeah, so first let me get the odds. That one, plus that one, plus that one, plus that one, plus that one. And then we multiply this one by 4. And then we also need in the formula the first part, first and last. So that's easy. There's first, and there's last. And then we need to add these together. So this is the total. Now that's not finished. What do we need to multiply our answer by? Multiply it by h, and then divide by 3. Whoa. Look at that. More accurate. No, but when I use the trapezoidal rule, what answer did I get for 10 pieces? 0.335. And this one's perfectly right. But if you really think about it, it should be perfectly right. Why? Well, what shape are we calculating the area of? A quadratic. And Simpsons Rule approximates the shape as a quadratic. So what you did was you took a quadratic and broke it up into quadratics. Of course it's going to be perfectly right. Maybe a little bit more interesting is if instead of using x cubed, we use something like x4. Okay? So let me just change this to power 4. So a very quick calculation here. Integrate from 0 to 1 x4. I should get, when I integrate x4 from 0 to 1, I should get 1 over 5, which is 0.2. If I use Simpsons Rule on x4, I get 0.20001. See it there? Much more accurate than trapezium rule. Can you see? If I did the trapezium rule 10 times, I don't think it would be accurate to 1, 2, 3, 4, 5. 5 decimal places. That's very accurate. Very accurate. So part of your assignment is comparing the accuracy of the different methods. Also comparing how quickly the answer is arrived at when you increase the n. So I think for Simpsons Rule, as you make the n bigger, you move quicker to the answer than with the trapezium rule. I think. This is what you need to look at. So what I'm going to do in the assignment is, I'm going to give everybody a function, a different function, and you have to use both methods on it for different values of n, and you're trying to see how quickly the method gets to the answer, which is more accurate, and so on. Yes? You get the idea? Is that yes? Okay. So that's Simpsons Rule. So it's very similar to the last lesson. I didn't do the part about the percentage error because I did that last time. It's the same idea. I need to give you the true value before you can know the percentage error. In your assignment, I'll give you the true value so you can calculate the percentage error of your methods. I'm encouraging you to use Excel for this assignment because you can see it's not more difficult to make the n bigger in Excel, you know. So I really do want you to try and use Excel, but I'm not making you use Excel. You can use other programs too. You can even use your calculator, because remember, your calculator has a table function on it. Do you remember that? No, you don't, of course not, because we did that. Of course, because we did that in semester 1, which was years ago.